Welcome to Lecture Online, and now let's take a look and see how we can use Gauss's law to describe what goes on in electromagnetic radiation. So we have a plane wave here, which is basically the front of a wave coming out of a dipole antenna. Far enough away, it looks like a plane wave, a flat wave coming out. So here's the front end of the wave, and of course that goes all the way back for a distance this way with electric field oscillations. Now we're going to draw a Gaussian surface around a small section of that, small enough so that the electric field strength here is basically the same throughout that particular region. Notice that the length of the box, that distance is equal to c times delta t. Remember, distance equals velocity times time, velocity speed of light, and a small amount of dt gives you the length of the box. The cross-sectional area would be a by a, so we'll make it a square box. And so you can see that the front surface does not have any electric field lines going through it, so the product of the electric field times the area in the front will be 0, and the back will be 0 again. So that's how we're going to approach it. So let's take Gaussian surface here. So we have the integral of the electric field strength times dA is equal to Q inside divided by epsilon sub naught. All right, so does Gauss's law fit electromagnetic radiation? Well, again, as we said, we're going to add up all the surfaces. We have the front and the back. So we have the strength of the electric field times the area for the front will be equal to 0. So for the front, when we do the integral right here, we get 0 plus the back. On the back also, since the electric field is straight up and down, does not go to the back surface, we get 0. The front surface here, or maybe the side surface on this side, that would also be 0 because there's no electric field lines going through the front surface this way or the back surface that way. So let's see here. So side on the left. So side on the left right here, that would be 0. And plus side on the right, that would be 0 as well. So far when we integrate the electric field strength times the area for the front, the back, the left side and the right side, we get zeros all the way around. Now what about the top and the bottom? That's where it's different, because to the top we have electric field lines going to the top in this direction, and to the bottom we have them going in this direction. So if we're now going to add the top, we can now say that it's the strength of the electric field multiplied times the area. And the area is going to be A times C delta T. So A times C dt, like that. That will be the multiplication of the strength of the electric field times the area of the surface. And now at the bottom, so here we have the electric field going out of the surface, so that's positive. At the bottom we have it going into the surface, so that's negative. So for the bottom, so plus the bottom, we have the electric field strength, but it's going to be a negative electric field strength times the area of the bottom, which is AC times dt. So notice that if we add all 6 surfaces together, we get 0 plus 0 plus 0 plus 0 plus these two terms, but they cancel each other out, so the whole thing is equal to 0. And we know that that has to equal the Q inside divided by epsilon sub naught. Well, since there's no charges inside, it's simply electromagnetic field disturbances. Therefore, we can say that 0 equals the Q inside, which is 0, and so the Gauss's law holds true for electromagnetic radiation in this format. And so therefore we can say that it meets all the requirements for Gauss's law, no violations anywhere, but it doesn't tell us anything. All it does tell us that there's no charge inside, so therefore we're good to go. On the Gauss's law for magnetism, it's the same kind of thing. Again, if we multiply the B times dA, and let me use a different color for that. So now I'm going to go ahead and do this integration right here. So if we look at the top and the bottom surface, realizing that the magnetic field does not go to the top and bottom, just to the left side and the right side. So let's see here, we'll use the same order right here. For the front, we get 0, plus for the back, we get 0. Plus the left side, there we do get something, because on the left side we have the strength of the magnetic field times the area, which would be A times C delta T. So it would be the B field, the magnetic field coming out, that's positive, B times the area, which is AC times dt. And for the right side, we have magnetic field going in. So here we have it coming out, there we have it going in. That would be negative magnetic field, so that would be minus B times AC dt like so. And then finally, we have the top and the bottom. There's no magnetic field lines coming out of the top, no magnetic field lines coming out of the bottom, so it would be plus 0, plus 0. And of course, that equals, well, according to Gauss's law, that must equal 0. And again, is that true? Sure enough, we get zeros everywhere, and this cancels out that, so that we end up with 0 equals 0. So both Gauss's law and Gauss's law for magnetism shows that there's no violation with Maxwell's equations on the electromagnetic radiation, at least when it concerns those two equations. But they don't tell us a lot. The bottom equation simply tells us that there's no monopoles inside the surface, causing magnetic fields to emanate, but none to enter. And secondly, we can see that Gauss law for magnetism, for Gauss's law shows that there's no charge inside the surface, that the electromagnetic field disturbances are simply due to some source outside the box, but nothing inside the box. So no charge inside. All right, now let's go look at some of the other laws associated with Maxwell's equations, which will tell us much more about electromagnetic radiation in the next videos coming up.